All right, so thanks for coming today. I'm very happy to have Terry Fong with us. I've known Terry for a pretty long time.
Long time.
Just catching up on his kids, who I met when they were this little. And they're all grown up now, I guess. So Terry is chief roboticist at the NASA Ames Research Center in California, in the Bay Area, where he's been since 2004. Prior to that, he was in the Virtual Reality and Active Interfaces group at EPFL in Lausanne, Switzerland. And before that, he was the VP of Development for Fourth Planet, a real-time visualization software company. He's worked in several research areas over the years, including space and field robotics, human-robot interaction, virtual reality user interfaces, and planetary mapping. Terry received his undergraduate and master's degrees at MIT and his PhD in robotics from CMU. Terry's a former director of the Intelligent Robotics Group at NASA Ames and has led several projects there, including developing the Astrobee free-flying robot, which was deployed to the International Space Station in 2019. He's currently the deputy rover manager for VIPER, a project to build and deploy a rover to explore the moon, which he's going to tell us about today. So, Terry, thanks for coming.
Great, thanks very much, Matthew. Good morning. I think technically it still is morning. Glad you all could be here today. I'm very excited. It's the first time I've ever come to TTIC. I actually grew up in Chicago out in the western suburbs, and for most of my life I thought of this as the University of Chicago, and I'm glad to find out that it's more than University of Chicago. Today I'm going to talk to you about the VIPER lunar rover mission that we've been working on for the past 5 years. I will tell you right now, I am sure that it's 110% different from the kinds of things that most of you spend your time thinking about here. I hope you'll find that interesting. This is a mission that's going to the moon, and what a better, I can't think of a better day to talk about a lunar mission than today. The fact that we are all going to head outside pretty shortly and go try to spot the eclipse. Actually, I heard yesterday on the radio when I was driving someplace that the moon is slowly moving in its orbit further and further away from the Earth, maybe like 3 or 4 millimeters a year, which doesn't seem a lot, but apparently in like 6 million years there won't be any more eclipses, total eclipses on the Earth. So we should be very fortunate. Enjoy it while you can. We have a very short period of time to enjoy it. As Matthew said, I've been at NASA Ames for 20 years, which I hear is about the same amount of time that TTIC has been in existence here. So in some sense we've kind of grown up together remotely. But I'm going to tell you about VIPER, which is the Volatiles Investigating Polar Exploration Rover. I take no credit for the horrible acronym, but that's the way everything is at NASA. If you come to NASA, the first thing you're told is forget English, you have to speak acronyms. So we speak VIPER these days, and this is the mission that I've been working on for the past 5 years. So to start with, let's go back a couple decades ago. 2 decades ago, the moon was considered a very different place than it is today, studied from the Earth. And from samples returned to Earth, especially during the Apollo era, the general thinking was the surface, it's pretty much the same. It's pretty much, bone dry everywhere. There might be a very thin exosphere, but, generally uninteresting. It's like a big rock in space. But that all changed with a number of missions, including one called LCROSS that NASA Ames launched, which actually impacted the moon, and we observed the plume from the collision of the impactor to the surface from places like the Hubble Space Telescope and lots of observatories on Earth. And what we now know is that the moon is a place that hosts all 3 forms of solar system water. That is water that might be internal to the moon, water that has been sequestered because it's been delivered from places outside of the, or beyond the moon, from asteroids and comets basically emplaced, and these superficial frosts that are due to the fact that the moon interacts with the solar wind and plasma interactions. But we don't really understand things such as the concentration, the evolution, in particular how is water retained on the moon over billions of years. We don't understand the distribution either laterally or vertically. Vertically is kind of interesting, the fact that the moon is constantly bombarded, and so things on the surface get churned up and can get buried over very long periods of time, so certainly over billions of years. And one of the big challenges that we have right now is understanding, not only the processes here, but whether or not these sources of water can serve as a resource. So the moon, instead of being a place that's just bone dry, this rock in space, is now viewed as potentially a really fascinating source of resources. And that has led to many space agencies, NASA included, wondering how do we find out more about this? And that, for NASA, has turned into the VIPER mission. So here's a short overview video, which I hope will play.
The future of human space exploration is being driven by the discoveries of existing the critical task of finding and mapping where water exists, what carbon is emitted, where the main growth can now begin. Leading us on that journey will be NASA's first mobile robotic mission on the moon, known as VIPER. Along with investigating polar exploration rovers, it will be the first to navigate the moon and the South Pole as part of NASA's commercial lunar payload services mission. This region sits just outside the western limit of the Greater and covers an area of 36 square miles. The first ever resource mapping mission on the surface of another celestial body, VIPER will roam the surface equipped with 3 seismometers and a drill to detect and analyze various lunar soil layers at a range of depths and temperatures. The rover will venture into permanently shadowed craters, some of the coolest spots in the solar system, where ice reserves have been preserved for billions of years. NASA had 4 critical parameters when choosing a landing site for VIPER: available sunlight, Earth visibility for communications from the moon to the Earth, data showing the potential presence of water and other resources, and terrain that is well suited for VIPER to navigate. The area to the west of the Helix crater met these conditions. Once on the surface, VIPER's mission will last 100 days and cover between 10 to 15 miles. While a baseline traversal route within a VIPER region has been identified, the scientific discoveries VIPER makes along the way will actually influence where the mission team sends it next. So its planned route will most likely change. During its first trip, VIPER will visit at least 6 locations where data suggests space could be found. By helping determine the locations where water and other resources exist, VIPER's findings will help pave the way for future landing sites under NASA's Artemis program. The prospects of achieving a long-term human presence on our moon never looked so bright.
So VIPER, as you saw in the video, is a mission to go to the South Pole of the Moon, or near the South Pole of the Moon, and spend about 100 Earth days prospecting. Our main thing that we're looking for, of course, is water, and in particular, subsurface water ice. But we're generally just interested in any sort of volatiles that we can find on that portion of the Moon. Now, one of the interesting things, of course, is that this is a very different kind of planetary rover mission that NASA has carried out previously. One of the big challenges here is that this is heading for the Moon versus Mars, and as much as it's been a real challenge to operate on Mars, the Moon's even worse. It's a much harsher environment. It's much colder. There's many more challenges in terms of things like the fact that we're going to a polar region, and so the illumination from the sun is at a very low angle. That leads to long cast, highly dynamic moving shadows. In addition, there's all kinds of challenges for going to a place where we know so little about the surface composition. And what that entails in terms of rover design is a question of how do you build a system for an area you know very little about. So it's a real sort of interesting, exciting, challenging mission. It also has a number of interesting facets to it, such as for the first time, NASA is depending upon a commercial launch and landing for its mission, something that we've never done before for a mission of this scale. And that also opens up all kinds of questions. In particular, if you think about sort of this overall big picture of lunar resources, if you're interested in the Moon, not just from a science point of view, but from an economic or even sort of architectural point of view, architecture in terms of future human space exploration, there's this whole sort of roadmap that goes from just making initial orbital observations, which we've done a lot of with satellite systems over the years, through prospecting and ground truthing, and then missions like VIPER, which kind of bridge the gap between what you can infer from orbit and what you need to measure on the surface, to the future where you can actually start taking advantage of these resources, extract them, mine them, and then make use of that. One of the big things here too is that VIPER is seen as a bridge mission, that is bridging everything which on the left has been fundamentally government-led in terms of missions to everything on the right, which is viewed as being commercial, so industry-driven, industry-led missions. If we go back to thinking about where is water ice at the lunar poles, as I said, the moon is now understood to harbor all three of these kinds of water sources. And then the question then is, well, if you're going to go with a short duration, that's like a 100-day or so mission, that has a short range, maybe 20-kilometer total drive distance, and therefore a short amount of operational time, how do you go effectively prospect for that? And so one of the things that the VIPER science team done is define what we refer to as ice stability regions. These are areas that have different characteristics in terms of whether or not we might find volatiles in deep areas, that is below 50 to 100 centimeters from the surface, in shallow areas which are closer to the surface, or even on the surface itself. And we use that to come up with an overall science measurement plan that drives the way that we plan out activities for the rover to explore. Now, one of the interesting areas that this mission is going to target are areas that are referred to as permanently shadowed regions, or as I said earlier, because NASA speaks in acronyms, these are PSRs. These are places where at high latitudes, so let's say close to the North or South Pole, the topography and the limited illumination from the sun creates areas that are permanently in shadow. As you might guess, these are extremely, extremely cold areas. The surface temperatures are in the order of 40 to 50 Kelvin. So, not a place you want to go camp out and have a nice day at the beach. But these are areas, because they're so cold, provide ideal conditions for basically sustaining any sort of water ice that might be placed there. To do this, we have been spending the past 5 years designing, developing, and building the VIPER rover. This is a system here that has to go and exist in these really radically different temperature regions, so we worry about how to do this with a fully electric rover. It has solar arrays, it has radiators, it has a number of different sensors for operations, navigation cameras, for example, on the front, as well as other sensors for localization and for operating throughout on the lunar surface here. As the video previously said, there are 4 instruments on here. There's a 1-meter drill, and then beyond that, there are 3 spectrometers, a near IR spectrometer, a neutron spectrometer, and a mass spectrometer. This overall rover system has been designed to be a combination of a mobile sensing platform, that is a system that's used to basically move prospecting sensors around on the surface, as well as one that can do sampling. It's not sufficient for us just to be able to take a spectrometer and basically move across the surface. We need to actually be able to pull up samples from the subsurface and look at those materials. As of today, the flight rover is 90% complete. We've been building it over the past several months. These pictures were taken, I think, last week here, showing most of the rover put together. It looks like a frame with a lot of, to be honest, what looks like aluminum foil. That's actually multi-layer insulation. It's a thermal blanketing material. We are in the process of putting on the solar arrays and the wheels over the next couple of weeks. And at that point, the rover will be fully assembled. That leads us to the next phase, which is integrated testing, which is going to take place over the next several months or so. And we hope that by early, so maybe like February or so next year, the system will be fully complete, fully tested, and all ready to launch, at least in terms of the rover. There's a lot more to be done for the mission because it doesn't make sense just to launch the rover. You actually have to design and prepare through testing and training the mission operations and the science operations, and that's also ongoing. By the way, if there are any questions, feel free to just interject at any point in time. Otherwise, you'll get to the end and maybe I've forgotten. Yes?
What's the temperature range?
For
the moon? So you say 40 Kelvin is the minimum. What's the maximum?
The maximum, actually that's a good question. I don't know what the maximum that we designed this for. It's actually driven partially by the environment where we have to survive. Because part of one of the things about this mission is that the rover is going to be on the moon for over 100 Earth days, which means it's going to extend through multiple lunar day-night cycles. So there'll be periods of time when it's in darkness and periods of time when it's in full illumination. Not always during those periods can we operate it because the rover has a direct line-of-sight radio communication system between it and the Earth. The other thing that really sort of constrains its operations in terms of temperature are the instruments or the components we put on here. So our camera systems, for example, they can't operate at 100 degrees C. I mean, they also need to be managed in terms of thermal. So I don't know what the exact.
How does
sort
that
of
compare to
range.
Mars?
So it's actually a much wider range than on Mars. To give you a comparison, there's a perfect segue here. If you look at past, on the top here are all the rovers that have gone to Mars. Back in 1996, the very first one was a very small Mars rover called Sojourner, and of course the rovers that you're more familiar with, the Mars Exploration Rover Spirit and Opportunity, the Mars Science Laboratory Curiosity, the Mars 2020 rover Perseverance. All these much larger systems, and of course they have 6 wheels and this interesting rocker bogie suspension system, versus VIPER, which you see in the bottom right here, which is more of a sort of compact rover with 4 wheels, but adjustable suspension systems. You also notice that one of the big differences between, especially like Mars Science Laboratory and Mars 2020, which are their plutonium-based power systems, VIPER is designed to be a fully electric system. So it uses solar arrays to get power from the sun, and then it uses internal batteries to hold the power to operate when you don't have sun. VIPER is a really new kind of planetary rover. It's designed for the dynamic lunar environment. You know, as I said, one of the challenges we have is that we have moving shadows and moving light. There are places where the shadow front can move as fast as 1.8 centimeters per second, which doesn't seem really fast until you realize that you might be sitting close to an edge and you have a solar-powered rover and you really want to make sure that you actually stay in sunlight. It's a big challenge, especially if there's any sort of slope or terrain variation to deal with. It's meant to also be a very high operational cadence. The Mars missions, they're at the end of a long communications path to Mars, which might be as the order of, say, 40 minutes round trip, just time of flight in terms of like the round trip radio communications. On the moon, we're talking round trip about 6 to 10 seconds. And so we can operate this in a very interactive, real-time fashion. And it's also been viewed, at least was viewed before the pandemic happened, as being a significantly cheaper rover. Like everything else, due to the pandemic, this mission has stretched out longer because our supply chains have stretched out longer, and because we've had to work in a different manner, and so it's been a bit higher cost than it was originally meant to do, but it's still significantly cheaper. Certainly, like maybe 1/5 the cost of a comparable Mars mission. I mentioned previously that it's interactive, so we have a design where we have mission operations taking place in real time. We have a real-time operations team, and I have to admit that I actually, beyond for the past few years, been the deputy rover lead, but the true reason that I got involved with this is that I really wanted to do the second job, which is actually, on the other hand, I'm actually the co-lead rover driver. So once it gets to the moon, hopefully I can put that on my resume. Hey, drove something on another planet or another planetary body. And as a result of this sort of interactive design and the fact that the mission is on the moon versus on Mars, and it's we have the ability of continuous communication when we operate. Our operations is more of a hybrid of human operations, the way that we've operated, for example, with the space shuttle or on board the space station, than with Mars rover operations. I won't go into details here, but if any of you are interested to learn more about the onboard avionics or software systems, it is actually not what I consider to be particularly high performance computing, unless anybody in this room is still using a 2010 iPhone 4. In which case, you know exactly how well this robot operates. I shouldn't say just that, because it does actually have a combination of both a radiation-hardened computer and a radiation-tolerant computer. And we've chosen to split the flight software between what's on board and what's on the ground, because we are in continuous communications, and we can do that, which we couldn't do for Mars. One of the other things that's interesting to note here is it has got a very different kind of mobility design. This is going to an environment which I said earlier is very unknown, certainly to us here on Earth, about what's the actual surface composition. It's going to have to operate in a place where you have lots of dynamic considerations in terms of temperature changes. And as a result of that, we tried to create a system which is very flexible, very capable by having adjustable suspension. So rather than the passive kind of suspension systems which we've used in the past for Mars, this one is adjustable. And we can do dynamic, real-time, continuous control of the overall suspension. Yes?
Sorry, the domain is unknown because of the shadowing.
It's because of the shadowing, because we've had through all the Apollo era, all those missions basically visited the equatorial regions of the moon. There has been nothing in terms of human exploration, and we've only had a single impactor mission to the high latitude portions. We're headed towards like 94 degrees south. Nothing has been there on the surface. So everything we know about the moon has been through remote observations. Just to give you a better idea of what this adjustable suspension looks like, this is one of our engineering prototypes. It doesn't look like a full flight rover because one of the big challenges we have is how do you build and test something like this on Earth? The easiest way to do that is to make something that's 1/6 the mass of the flight rover so that we can just test it in Earth gravity without having to do any sort of gravity offset. But that means we have to basically throw away everything that we don't consider to be very much required for testing mobility. So there's no solar arrays or no instruments on here. It's just the drive system here. And this adjustable suspension system allows us to do all kinds of interesting things with the chassis. We can independently control each of the suspension arms here, so we can do push-ups. We can do interesting driving things, so it's not just in terms of using wheels and turning, but we can also do things like wheel walking and inchworming, and I'll show you some more videos later on. But it's a very capable system. It's more complex than the kinds of systems we've sent to Mars, but it also gives us the ability to perhaps deal with some of the things that we cannot right now foresee as occurring during the mission. We've spent a lot of time doing testing over the past few years. This is an example of wheel prototype testing. The wheel design itself is a huge area of specialization, just in terms of how do you design the overall structure of the wheel. In this case here, it looks like bicycle tires, so there's metal spokes here. On the outside of the wheel are grousers to help it grip as it's going over loose terrain and be able to climb rocks. Done an extensive testing campaign just on the wheels itself. Something that's highly specialized. I would challenge you to find more than maybe 3 or 4 places in the world that's focused on design of wheels for planetary rovers. Not really the kind of thing you can easily go get a job in. We've done testing in a number of facilities that are quite interesting as well. This is one called the Slope Lab, kind of obvious name because it's got this big tilt bed on here. This is actually at NASA Glenn in Cleveland. It's a place where we have the ability to put rovers through a variety of different challenging conditions. You can change the slope angle so you can drive all the way up to the angle of repose for various materials. In this particular case, the simulated soil is a soil called GRC1, Glenn Research Center 1, which is meant to be a high-fidelity terramechanical simulant of the lunar soil, at least in terms of terramechanical properties, not in terms of appearance or in terms of, say, neural content, but in terms of the way it behaves terramechanically. And so we've done testing in this facility. That
Is that why they're wearing the?
Yeah, it's very, very, very fine grains there, and it's easily levitated. You can see the powdery kind of dust coming up here. It's not kind of thing you'd like to breathe in, and so people have to wear respirators when you're operating around this material, especially if you're kicking up lots of dust, like rovers tend to do. So we've done testing involving things like, can we entrap the rover? Can we get it really stuck? Which is the fun part. Basically put rovers through torture chamber kind of testing, and that can also involve having to look at can we make it slip? Can we get into a place where we're just not making any forward progress? This is a testing with an older engineering prototype here, and of course we take a lot of high-resolution metrology when we're doing this to try to understand just the overall performance of the vehicle under various test conditions here. In this case, it's really focused on slip. We also take a look at some of the terrain hazards that we're likely to encounter, such as positive and negative obstacles. The most common negative obstacle, of course, are craters, but because we are very concerned about the composition of the soil and whether or not they may be very uncompacted, unconsolidated materials, a big challenge is how do you drive through that? How do you avoid getting stuck? And so that's occupied a lot of our time. And one, answer to that how to avoid getting stuck is to look at alternative mobility modes. So not just driving with wheels and turning the wheels, but looking at combinations of suspension control along with steering and propulsion. So you end up with all these kind of interesting gaits, which you think of these as kind of inchworming or wheel walking or swimming. We've done a lot of testing for how these different kinds of gaits could provide you with a useful way to get out of a really bad situation. Now, of course, one of the questions I'm often asked is, well, why don't you always operate like this? Well, I will say the reason is this is really hard on the drivetrain. We generally don't build, for example, ground vehicles that are designed to swim. for good reason. It makes it really hard in terms of the actuators and the gearing, especially in highly dusty environments like here where you're worried about dust getting into the places where dust really shouldn't be, that is, within the gears. Yes?
Is there a way to right itself if it gets knocked over?
No, unfortunately, if we manage to flip it, then it's game over. That's one of the reasons why, in terms of the design, we specify that we can, and we've tested up to 15-degree slopes. If we determine that areas are going to be higher than that, or if we inadvertently end up on a slope that's much steeper than that, and there is a risk for us flipping over, then that's going to be a real, problem. It'll probably be the end of the mission at that point. That said, the overall design of the system is that most of the mass is focused way down here. So in general, we're not too concerned about tip over, and we're not driving fast enough to really worry about sort of dynamic tipping. Yes?
Is this car fully teleoperated? Is there any automatic driving system inside?
I'm gonna get into that, but just the short answer is it's a combination of things. We don't control it like you would control like a radio controlled car. We are sending it position-based commands, and the rover basically moves from point to point. It also has the ability to, if it loses communications for an extended period of time, to automatically try to recover by moving to a place where we believe that there should be good communications. Part of the challenge for this mission also is at the very start. Is how do you get off of a lander? The lander that we're planning to go to the moon on is actually made by a spin-off company from Carnegie Mellon called Astrobotic. They're a small company in Pittsburgh, and their lander, the Griffin 1 lander, of which is a mock-up here, will land through rockets on the surface, come down very slowly, and then ramps will deploy, and we'll have to then drive off the ramps. So a fair amount of our time has been spent trying to understand, well, what are the likely possibilities for just getting off the rover? Do we have to worry about, for example, the rampways splaying or being, bowed in some way, or the ramps being, offset? And so that's another reason why having an adjustable suspension gives you more capability to deal with problems, such as the rampways having been deployed with some sort of problem. Other testing that goes on, at NASA are things for this mission which are really unique. The fact that we are in continuous communication with Earth means that we always have to point our high-gain antenna at the Earth. And so that seems fine if you're not moving, but it's a rover mission, so you're going to be driving, going over bumpy terrain. And so we've spent a fair amount of time with a pan-tilt gimbal system that points the antenna and doing a lot of design of the control systems for measuring the rover's state and then being able to use that to then basically dynamically point while the rover is moving. And so being able to take out all the bumps and shakes that occur as you're going across terrain. In these videos here, you can see the rover either being rotated around or actually driving over terrain. And the top right here, this is actually a video that we recorded with a camera mounted at the high-gain antenna gimbal. And in the center there, we automatically detect where the moon is, and we can keep it within that ellipse here. That means we're within the error boundary for the pointing. Now this testing was actually really good to carry out because it's actually much harder to point at the moon, which in the sky is much smaller in terms of the distance it subtends, than the reverse when we're on the moon and pointing back at the Earth, because the Earth is much larger. But this gives us confidence that we can maintain communications while under motion. This mission is also the first to actually have a rover that carries its own lights. We've always had that pleasure on Mars operating during the daytime, but because this mission is going to the moon into areas including permanently shadowed regions, we have to carry our own lights for supplemental illumination of the terrain. And so we've done testing, especially at nighttime. This is actually outdoors at NASA Ames in California, where we use an incredibly bright sun simulator that we built just for the purpose of trying to simulate the sun in a controlled manner. And we've looked at a variety of situations such as what do positive features like rocks and what do negative features like craters or slopes in certain configurations look like as you're operating in the nighttime. We've also built and spent a fair amount of time characterizing our cameras and lights in a facility which we call the Lunar Lab. It's a very uncreative name, but it's a large 4 by 19 meter sandbox that has 19 tons of LHS-1. It's a different kind of lunar soil simulant. This one is high fidelity in terms of its appearance, and of course this is very important for all the computer vision work that we do with the rover. And so this facility here, as you can see here, is one where we constructed in scale different terrain features, and we have a scaled down sun illuminator If you fly with the camera over the surface, it actually looks quite realistic. But again, this is all just within a lab flying over basically a large sandbox.
There's no LiDAR, it's all vision.
Right, so the rover is equipped with a total of 8 cameras. We actually have a stereo pair on a pan-tilt gimbal on the front, that's our primary navigation sensors. We have a stereo pair pointing aftwards, and then we have 4 hazard cameras, 1 at each wheel, to give us views of what's going on with the wheels at the terrain. That takes me to a topic that might be of interest to some of the people here, especially if you're involved in planning. We have a large, difficult problem here, which is this is a relatively short duration mission in an area that's highly uncertain, where we need to make a certain amount of measurements given a limited amount of time, given more resources. And so the planning problem, in terms of automated planning, is a really interesting, challenging area to work in. We have a team of people that have been working on developing activity, resource, and traverse plans. So there's both temporal constraint planning as well as motion planning has to go on here. We do this both in a strategic and tactical sense, because this mission has to consider the fact that we will discover things as we operate and then have to then replan in real time. And in particular, because we're concerned about how long can we actually operate, how do you do this in a way that can achieve full mission success, full science success, when there's significant uncertainty? And it's an interesting problem because there are a lot of constraints, and these are only a few of them. Having to worry about how do you measure the distribution and state of this unknown set of volatiles, unknown resources, where they actually are. A solar-powered rover with limited battery means limited time that you can operate in the shadow, or limited amount of time that you can survive lunar night. The fact that we're in these kind of interesting summer seasons where the geometry of the moon and the Earth are favorable to a mission like this, which is solar-powered and has to have direct communications to the Earth. The fact that you have line-of-sight communications to the Earth, the fact that you're limited in how far you can drive, in this case 20 kilometers. It's actually a pretty large distance for this duration of a robotic mission, but 20 kilometers is nothing. I mean, I think most of us probably drive far more than that even just today, a single day. The fact that the slopes have to be considered, step obstacles have to be considered, drive speed while prospecting, which is limited by instruments, and moving shadows. These are like only a few of the constraints. And so you throw all these together, and you have this big problem of, well, how do you deal with that? Oops, I just lost the projector, I think.
The dongle. Wiggle the dongle.
I didn't do anything, actually.
No, it's like
Should I unplug this?
Yes, thank you.
Let's try that.
Although it's reversed.
Displays. Yeah, except I can't.
You can swap display just here.
I can't actually see it over here. Find my cushion out.
Oh, there you are. Down you go.
No, actually, that's not correct. I didn't do anything.
the eclipse.
Shadow.
Shadow.
Yes,
And the ghost.
the permanent shadow.
We're in permanent shadow now.
Yes.
Currently.
Does someone have another dongle?
It was there, so it should be mirroring right now.
Did they grab a dongle, Adam?
Yeah, do you have a spare one?
Yeah, it went downstairs.
I switched to mine. Just want to try HDMI. Okay, I think we're in business. Okay, as I was saying, we get into a very challenging planning problem. And if we break the planning problem down, there are four main areas we have to deal with. One is we have to have good data sets to work with. And so for this kind of mission, the key part of that is developing high-resolution digital terrain models. That leads into science and mission planning models, which have to do with understanding limitations of communications, illumination, ice stability in these different regions we're looking at. We go into strategic planning and tactical planning. Just to give you an idea, I have no idea if anybody works in terms of digital cartography stuff here, but one of the most interesting things over the past couple of decades within NASA and places like the USGS has been the use of automated photogrammetry for planetary surfaces. And in particular, trying to make use of a variety of instruments, such as laser altimetry. For the moon, you might be able to end up with digital terrain models that look like this, say 5 meters per pixel. But that's through very sort of sparse observations. Each of these green dots are places where you have basically a laser altimetry reading. And everything else about the surface between those readings is interpolated. If you look at the best available photography you have, you might be able to get down to 1 meter per pixel. And that seems very high resolution until you look at a rover which has basically a footprint of about 1 meter. And so you're going, well, okay, so it's very blocky on the scale of a rover, not so great for planning and operations purposes. So NASA aims, part of what we've been doing is working on shape-from shading methods or photogrammetry methods to try to end up with higher resolution maps that are a fusion of laser altimetry plus photography, but getting to higher resolution. And that gives us a good set of data to work with here. We end up with very high resolution terrain models here that are about 1 meter per pixel, but this is actually the same resolution as laser altimetry, but it's not just interpolated. In terms of strategic planning, that involves this whole consideration of a whole bunch of different things. Various inputs in terms of what are feasible traverses that you could carry out, in terms of things that satisfy some of those constraints I said before. You end up going through a variety of processes to basically identify classes or related groupings of templates of traverses to then evaluate here. You may actually have to then generate a number of different hypothesized traverses that meet certain specifications, and you have to evaluate that all together in terms of whether or not these traverses are sufficiently robust to variations in, for example, timing. Because if you choose, for example, a traverse which looks perfect, but the reality is if you're not exactly there at the right period of time, then instead of being light, you might be in shadow. So you have to really kind of understand the overall sort of margin associated with traverse planning. That leads into tactical planning, which is very detailed analysis of things like the actual time of activities. And you have to combine a variety of different conditions and constraints, such as the locations, with the time that you're at the locations, both when you arrive and when you leave those locations. And you end up generating all kinds of detailed tactical timelines here, which are then analyzed, again, for their robustness to uncertainty. At the end of the day, what you end up with are things like this. This is an example traverse plan. The red arrow there is moving, showing where the rover moves, and it's playing this kind of game of trying to basically follow the sun and avoid the shadows. So we'll go to places and sometimes stop for extended periods of time because you're waiting for the sun to catch up or the shadows to run away. This is a highly interesting problem, which the people who work on the planning team have spent a lot of time, looking at different automated solutions, and we lost the predictor one more time. Oh, it came back, or not. I don't know. I guess there must be some big eclipse or something happening today. In any case, hopefully we can get through the next 15 minutes before we lose the predictor again. So that's one aspect of the project. Another interesting aspect is in terms of simulation. Because we're designing a mission that's going to some place that we've never been before with a robotic mission, there are big questions of how do you design and test for that. And so a key part of our strategy has been developing high-fidelity simulation systems that could be used for engineering testing. So we basically create the simulator that is used as part of our testing. But then we also turn around and use that same simulation system to support mission operations training. And part of this has to do with creating systems that can run in real time, that have high fidelity, as high as fidelity as we can actually accomplish and still operate in real time. And so we've spent quite a bit of time developing a lunar surface simulator. It's actually derived from Gazebo, if any of you are familiar with that. The roboticists in the room probably are very, very familiar with that. And we added a lot of different features. We've actually worked very closely for many years with people at Open Robotics to extend Gazebo from what it's been used for terrestrially into a system that's suitable for lunar surface simulation. And that includes things like high dynamic range rendering, real-time shadowing, Rover wheel tracks, slip modeling, all kinds of interesting things like that. We've also spent some time generating pipelines for creating synthetic, higher resolution lunar terrain that we can create from actual orbital data. So I showed you, some of the slides before about modeling 3D surface. That only gets us to about 1 meter per pixel. We'd actually like to be higher resolution for simulation purposes and for testing purposes. And so we've created our own synthetic terrain pipeline to generate 4 centimeter per pixel, 4 centimeter per post synthetic terrain that's still plausible. So it's not an accurate representation of the lunar surface, but it is plausible in terms of science and in terms of our understanding of the physical processes that govern the way the lunar surface actually is. The synthetic DM process involves starting with actual real data. So we'll start with lunar reconnaissance orbiter camera imagery, that's the LROC NA imagery, and laser altimetry, generating additional DEMs, digital elevation models. There might be 1 meter per post using the shape from shading technique, and then we'll enhance that by adding higher resolution features to come up with plausible synthetic terrain that we can use for testing and training purposes. And so you end up with results like this. This is a synthetic terrain, but again, it's originally derived from actual orbital data at lower resolution. And we can use terrain like this for both testing things like our computer vision systems and for doing operations training, where we teach the operations team how to deal with environments like this. You can also see representations of a variety of craters here. We follow interesting models of the size frequency distribution for both rocks and for craters and apply that to generate these terrains. This is a video here actually showing you, I would show you if I could. All right. Well, in 1 segment, snapshot, you can actually see us flying over the moon here. This, by the way, is real-time rendering of the synthetic models that we generate here. I actually have no idea what's going on, because it allows you not touching anything here.
Is it tight in there?
Yeah, but it's working sometimes, so I don't know. It seems like your projector is just not happy with what this Mac is outputting.
You can try this.
Okay.
Usually what works is if the wire is hanging outside that sliding deck, at least from my class.
If it's what?
Maybe you can.
Oh, you're using directly the
HDMI,
It's still
yeah.
having this system.
Yeah.
Oh, then this is not going to answer that.
Yeah.
I thought you were using
No.
HDMI to down.
This just disappeared here. Is that
See,
better?
your mouse is
that's
not going to be any
your
better than
mouse.
this.
Pointer.
But you're welcome to try it. I thought you were using it.
Okay.
I've had issues with that when I teach. So I use either HDMI directly into my lab. Actually, that's what I usually do.
Okay.
Yeah.
Let's see.
Oh, okay. All right, dog number 3 is definitely working. Again, this is a video of the synthetic terrain that we generated. In this particular case, we're using this as part of the Rover simulator that we've built to operate in real time. You can see there's real-time shadows. We have very high resolution terrain here, far higher resolution than you would get from orbit. And we use this. Oh, so close.
It's okay. It's back.
It's back. Okay. Let me move on. I'm trying to get through the last few slides here, then we can talk more. Okay. So the last bit about this talk is just talking about mission operations. This mission is going to be fully interactive between Earth and the Moon. As I said, we expect to have between 6 to 10 seconds round trip latency. The variability there really actually has to do with the ground station on Earth delays and buffering. We operate this through what's known as the Deep Space Network. This is a set of network ground stations, large antenna dishes around the world that receive communications from deep space. In this particular case, deep space is only as far as the moon, but then they are then relayed the data terrestrially across ground networks to our Mission Operations Center. This is an example of mission operations simulation that we ran a couple months ago. This is in our primary mission operations control room. It's a relatively small control center. This is based at NASA Ames, where we have 2 rows of operators here. These are the primary operators of the Rover mission, and then there are a number of other mission operations rooms that focus on things like instrument operations and science operations, and they're scattered not just at NASA Ames, but also at 2 other NASA centers, NASA Johnson in Houston and NASA Kennedy in Florida. In fact, the overall mission operations is meant to operate with these distributed set of control rooms, all working together and then talking to and from the rover across the single high-gain communications link. And when I say high gain, that's really in terms of the signal. It's not high bandwidth. I didn't say high bandwidth, I said high gain. We expect to operate at minimum having 256 kilobits per second, which for the only people in the room, that used to sound fast, and now it's sort of like something you don't even talk about. We do actually believe that we'll have higher bandwidth than that, but our design is designed to focus on being able to operate even if we only have that. And then what we do in terms of operations is once we get off the lander, we drive from the lander location to the first science station region. That section of the drive is really focused on just getting from point A to point B. And within the science station, we end up doing traverses that may be sort of lawnmower pattern that include drilling at various locations for sampling the subsurface. The overall sort of key science measurement goal here is in terms of accruing measurements over distance and trying to have as much spatial diversity in the measurements to help build our understanding of the, as I said, the horizontal and vertical distribution of resources. This is an example of one of the rover driving interfaces. This is an interactive 3D user interface that displays a number of different things. You can see in the center, the main 3D view here is a representation of the hazard map of the area. Hazard is in terms of how hazardous it is to actually drive the rover across that area. So green means that it's, for example, might be low slope, low roughness, minimal steps. Red means it might be steep or could have significant sort of step discontinuities. And we use 3D rendering here to provide the operators with a better understanding of the 3D terrain. We also overlay information from cameras as well as other sensors in this interface here. What we end up with here is on the left here is that same interface you saw. In this particular case, the operator is going to lay out a waypoint that says drive, in this case, about 8 meters forward, and it's a little bit to the right of the rover. On the right side is the simulator that's running in the background here, so the operators don't get to see this. It'd be nice to be on the moon and see this thing. But you can see that after you command the rover on the left, some period of time later, 6 to 10 seconds, the rover starts moving and data from the rover gets sent back down to the Earth. So this is the kind of interactive but time-delayed operation that we focus on from a rover operations point of view. Beyond this, there's a lot of details in terms of how each instrument is done and the fact that we have to operate in a real-time science mode, which is really different for NASA. Typically, we focus on just rover operations and downlink the science data, and then it's analyzed not in real time, but for weeks at a time. Here, a lot of the analysis happens in real time. And in fact, the operations design has one of the mission scientists sitting in the position that we call RT-Sci, or real-time science. In some respects, it's a lot more similar to the kinds of things you see on the oceans today. If you go out and sit on a ship that's run by like Hui or Mbari, you'll see somebody a scientist sitting alongside an operator like an ROV and interacting in real time. Well, that's a lot like what we're doing here with VIPER. But with that, let me wrap up since we're at 12:21, and I'm sure you must have some additional questions, and I don't want to, jinx the projector. So stop here. Yes, Matthew.
So do I understand correctly, you're using shape from shading in 2 different ways, both with the aerial coarse photography imagery and the cameras on the device?
No, we are really only doing the first part. We're really basically using photogrammetry to improve our generation of 3D terrain based on orbital data.
So what kind of vision is being used for the cameras on the device?
So on the rover itself, we have total 8 cameras. All of the vision processing is actually done on the Earth. So we do some amount of onboard processing. We'll do some onboard rectification, and in the case of for stereo processing, we use very old techniques. I mean, there's some slog conversion that happens on board, and then we downlink those images because they can be highly compressed. And we do basically stereo correlation on the ground, and then that feeds into a number of things that we do with that. Part of it is localization. So we do 3D to 3D point matching as part of ground side visual odometry. We do hazard detection, and we generate these HAZ maps by basically interpreting various 3D point clouds and applying various metrics for terrain classification. And that's done on the ground side. And the results of that then feed into operator interfaces because this is interactive. In general, we don't close the loop just fully automated with the rover. In fact, all that processing feeds in as like decision support tools to the operators. And that's just because this mission is being operated in a very interactive manner. Of course, it'd be very easy from a robotics point of view just to close the loop completely, even if it's done through the Earth. But the fact that we are, operating this not as a robotics mission, but as a science mission, which is, one of the things I actually was really surprised when I first went to NASA. I was like, oh, I'm going to NASA, I'm going to build robots. We're going to have robotic missions, and guess what? Robotics is the way that you get the science instruments to where they need to go. It's not because you're trying to build a robot. It's because you're trying to get the science measurements. And so as a result of that, even missions like VIPER, the interactive design is focused on what kind of science measurements and interpretation can be done in real time. And so rather than fully close the loop, robotically, you feed this into an operations team, which includes real-time science.
And what are the classes that terrain gets classified into?
So it's interesting in terms of the classification. We went back and forth for quite a while about whether or not we wanted to apply just locomotion metrics to terrain to say, okay, well, we designed it to be able to handle 15-degree slopes, so we should focus on just binary classification of whether or not it's less than or greater than 15-degree slopes. But we ended up focusing on an approach that's really driven by the way NASA typically approaches missions, which is in terms of risk. So we classify the terrain into actually 4 classes of risk, where class 1 terrain is considered benign. You can drive anywhere, nobody needs to be able to pay attention, it's super easy. Class 2 is considered to be a little bit more dangerous, so you should spend a bit more time. So maybe class 1 is like you're on the open highway. Class 2 is, okay, now you're getting off the highway. Class 3 is an area where you want to have a lot of consideration because you could lose the mission, but you can still drive there. So it's like driving through Chicago traffic, I guess. And class 4 is, okay, now you're in a really bad situation, so you basically run off the road. How do you get out of that situation? So it's really risk-based terrain classification. Yes?
Was there ever a discussion on using legged robot rather than wheel-based robot?
In terms of this mission, we didn't really take a look too hard at whether or not we should look at legged locomotion, primarily because it's always been considered that wheeled locomotion is more power efficient, especially when you end up standing still a lot of the time, which is the case. This mission, will operate the rover at the lightning fast speed of 20 centimeters per second. That's the highest speed, okay? But in general, the overall average rate of progress, the speed made good, is on the order about 1 centimeter per second. So it's a very slow-moving mission. And that still is like 5 or 6 times faster than anything on Mars. Yes?
Does it cost more to build the robots or to send it there?
I'm sorry?
Or does it cost more to build the robot or does it cost more to send it there?
It costs more to
build it or
robot,
send it.
or to send the robot. It's definitely costs more to not only build the robot, but build, test, and then plan for mission operations than to send it. Although, I will say that part of the reason is because NASA is trying to make use of what's called the CLIPS program, the Commercial Lunar Payload Services Program, which is this idea that NASA or any customer is basically just paying for transport. So the development of the lander and the launch vehicle are all done on the commercial side. NASA doesn't actually have any direct involvement with that. In this particular case, we put out a request for, hey, somebody would like to send this robot to the moon. And we got a number of responses. Astrobotic was viewed as being the best value for the government in terms of the cost and the risk and the maturity and all that kind of thing. And so Astrobotic is the one responsible for basically picking up the rover, essentially picking up the rover in Florida and depositing it on the moon, at least the lander. And because of that, we have a fixed price contract with them. And so no matter what their cost is, we're just paying the best value. It's sort of like the FedEx or UPS model to the moon.
Is that Red Whitaker's?
It's a spin-out. Well, Red Whitaker was like the chief scientist in some way, but it is a spin-out with a lot of people who used to work for Red in the Field Robotics Center in Carnegie Mellon. They're located like 2 miles away from CMU. Yes?
Did you ever consider the option of sending several rovers with the same mission to minimize risks?
Yes, we did. There's been this large and ongoing debate about the value of multiple robots, whether or not they coordinate properly, even just for redundancy purposes.
To minimize risks.
Yeah, to minimize risks. And in theory, then you should be able to build the second and third and fourth copy cheaper.
That's what
I will say though, when this mission started, one of the sort of ground rules was, okay, we should do this mission as fast and as cheaply as possible, which kind of like took all the discussion about, doing more than one off the table. In hindsight, because of the delays we've had because of the pandemic, particularly the pandemic, that would have changed a lot of things about our overall design. Maybe we would have built a second rover, but this is a single rover mission.